Have you ever wondered why power transfer matters so much in electrical engineering? It's a question that can unlock a world of understanding about how our modern world operates. Today, we're going to peel back the layers of this fascinating topic and dive into the heart of power transfer. It all begins with a principle known as the maximum power transfer theorem. This theorem, which is a cornerstone of electrical engineering, states that for maximum external power to be obtained from a power source with internal resistance, the resistance of the load must be equal to the resistance of the source as viewed from its output terminals. This is not just a modern idea. In fact, it dates back to the mid-19th century when a man named Moritz von Jacobi published the maximum power transfer theorem. This theorem, also referred to as Jacobi's law, has shaped the way we understand and utilize electrical power ever since. But here's an interesting fact. The theorem doesn't result in maximum efficiency of useful power out of total power consumed. Instead, it focuses on the maximum power transfer from the source to the load. If the load resistance is larger than the source resistance, efficiency increases, but the magnitude of the load power decreases. If the load resistance is smaller, then efficiency decreases, but the total power dissipated increases. The theorem is all about how to choose the load resistance, given the source resistance. It's a common misconception to apply the theorem in the opposite scenario. In reality, the source resistance that maximizes power transfer from a voltage source is always zero, regardless of the value of the load resistance. The power of this theorem extends beyond just electrical circuits. It can be applied to alternating current circuits that include reactance, stating that maximum power transfer occurs when the load impedance equals the complex conjugate of the source impedance. It also has applications in other physical interactions, such as mechanical collisions, charge sharing between capacitors, liquid flow between cylinders, and the transmission and reflection of light at the boundary between two media. Now, let's delve into the theorem and understand its workings. Let's break down the maximum power transfer theorem in simpler terms. This theorem, published around 1840 by Moritz von Jacobi, states that to obtain maximum external power from a power source with internal resistance, the resistance of the load must equal the resistance of the source as viewed from its output terminals. Let's dive a little deeper. The crux of this theorem lies in the concept of load and source resistance. In the world of electrical engineering, the source resistance is the inherent resistance within the power source. On the other hand, the load resistance is the resistance of the device or component drawing power from the source. Now, why is it important that these resistances are equal for maximum power transfer? Well, if the load resistance is larger than the source resistance, efficiency increases. This means a higher percentage of the source power gets transferred to the load. However, the magnitude of the load power decreases because the total circuit resistance increases. Conversely, if the load resistance is smaller than the source resistance, then efficiency decreases. Here, most of the power ends up being dissipated in the source, and although the total power dissipated increases due to a lower total resistance, the amount dissipated in the load decreases. This brings us to a common misconception about the application of this theorem. It's important to note that the theorem instructs us on how to choose the load resistance once the source resistance is given. It's not the other way around. The theorem doesn't tell us how to select the source resistance for a given load resistance. In fact, the source resistance that maximizes power transfer from a voltage source is always zero, regardless of the value of the load resistance. So we see how the theorem dictates the choice of load resistance for maximum power transfer, not the other way around. What happens when we change the load resistance? Let's find out. In the realm of electrical engineering, the resistance we place on the load can significantly alter the efficiency and magnitude of power transfer. Now, you may ask, how does this work? Well, let's dive into the math a bit. Consider for a moment a power source with a fixed internal resistance. Let's call this Rs. Now, if we connect a load with resistance RL to this source, the efficiency of our system, represented by the Greek letter eta, is the ratio of power dissipated by RL to the total power dissipated by the circuit. This efficiency can be expressed as 1 divided by 1 plus Rs over RL. Now let's take a look at three specific scenarios. First, if RL over RS approaches 0, our efficiency also approaches 0. This is because in this case, RL is much smaller than RS, making the load essentially a short circuit. All power is consumed in the source, leaving none for the load. Second, if RL and RS are equal, our efficiency is 50%. This is the condition for maximum power transfer, as established by Jacobi's law. However, note that while power transfer is maximized, efficiency is not. Third, if RL over RS approaches infinity, our efficiency approaches 100%. This happens when the load resistance is significantly larger than the source resistance. While this does increase efficiency, the total power transfer decreases because the overall circuit resistance is too high. So this creates a delicate balancing act. If we want to maximize power transfer, we need to match the load resistance to the source resistance. But if we want to maximize efficiency, we need to make the load resistance significantly larger than the source resistance. Understanding this relationship helps us optimize power transfer and efficiency in electrical circuits. This is the heart of the maximum power transfer theorem and its practical applications. By tweaking resistance values, we can tailor our circuits to prioritize either maximum power transfer or maximum efficiency, depending on our specific needs. The maximum power transfer theorem isn't just about circuits and resistances. It applies to many other physical interactions too. This theorem is like a universal translator in the world of physics, bridging the gap between different domains. Take alternating current circuits, for instance. You might remember the theorem stating that for maximum power transfer, the resistance of the load should equal the resistance of the source. Well, in alternating current circuits, things get a little more complex. Here, the theorem states that maximum power transfer occurs when the load impedance is equal to the complex conjugate of the source impedance. But let's step away from circuits for a moment. The theorem also extends to mechanical collisions between two objects. Just as in an electrical circuit, maximum energy transfer between two colliding objects occurs when their mechanical impedances match. The theorem provides a mathematical framework to analyze and optimize these interactions. Are you surprised? Well, hold on to your hats because we're just getting started. The theorem also applies to charge sharing between two capacitors. Picture two capacitors, one charged and the other uncharged. When they are connected, charge flows until an equilibrium is reached. The maximum power transfer theorem can be used to analyze this process. What about the flow of a liquid between two cylinders? You guessed it, the theorem applies here too. The flow rate and maximum power transfer can be optimized when the hydraulic impedance of the two cylinders is matched. Finally, consider the transmission and reflection of light at the boundary between two media. The theorem can be used to maximize power transfer and minimize reflection by matching the impedance of the two media. So, whether it's electrical engineering, mechanics, fluid dynamics, or optics, the maximum power transfer theorem has got it covered, providing a unified theory to optimize energy transfer across different domains. Isn't it fascinating how one theorem can explain so many different phenomena? Let's recap what we've learned about the maximum power transfer theorem. This fascinating concept, published by Moritz von Jacobi around the year 1840, posits that for maximum power transfer from a power source with internal resistance, the resistance of the load must equal the source resistance. It's a cornerstone of electrical engineering, highlighting the delicate balance needed to optimize power transfer. Remember, this theorem is all about maximizing power transfer, not efficiency. If the load resistance is larger than the source resistance, we see an increase in efficiency but a decrease in power. Conversely, if the load resistance is smaller, efficiency drops while the total power dissipated rises. It's a dance of give and take, a delicate balance between power and efficiency. One common misconception is to apply the theorem in reverse. To clarify, the theorem guides us on selecting the load resistance given the source resistance, not the other way around. In an ideal world, the source resistance that maximizes power transfer is 0, but that's not often feasible in reality. The theorem doesn't just apply to direct current circuits. It extends to alternating current circuits involving reactance, stating that maximum power transfer occurs when the load impedance equals the complex conjugate of the source impedance. It's a versatile theorem, applicable in a wide range of scenarios, from the collision of two objects to the flow of liquid between cylinders. We've also delved into the efficiency ratio, which is the power dissipated by the load resistance compared to the total power dissipated by the circuit. If the load resistance approaches zero, efficiency approaches zero. If the load resistance equals the source resistance, efficiency is 50%. If the load resistance approaches infinity, efficiency is near 100%, though the total power level tends to zero. So the next time you see an electrical device, remember the complex and fascinating principles at play. Thank you for joining us on this journey into the world of electrical engineering.